you see Maddie's message to you?
So why am I going over notes in midterm for people who ditched my class?
I
Well, so I mean, maybe I'm thinking at the end, after we're finished doing this, what we do is we pause the video.
Please don't, because I have to get up really early, so I was thinking about leaving.
So we're dropping like flies, is what you're saying? You know, I have a 7 a.m. meeting.
Yeah, I have a meeting tomorrow morning too.
Huh? 6 a.m. class? What class? You have a class? You have a Spanish class at 6 a.m.? Or is that a rescheduled thing, like the teacher meets then?
No, it's like every Monday, Wednesday, Friday.
At 6 a.m.?
Yeah.
That can't be right.
It's not. No joking.
Oh.
The earliest I've heard was 7:30.
Yeah, so we'll have to see. We'll have to see what mood I'm in towards the end as we drop like flies as to whether or not exam review gets recorded.
Okay, because I have a meeting with my boss tomorrow.
I get it. You're all adults. You can make your own decisions. All right. So let's see. Okay, so we are writing our read here for our horizontal composite memory, right? So we're going to go through here and we are going to collect our bits. So we're going to go through all of our memory, asking each one. We're going to do a read from that particular memory. Now remember, this read's only going to work if the memory is in the right state. So we are still going to have to set the state like we did before, but that's going to be the next thing we read. Okay, so assuming we are able to do a read here, which is assuming that read is enabled, we're going to create a storage location for our bits. We're going to have a storage location for our decimal value. Go through each memory, ask the memory to read the decimal value. Then we will pad that decimal value to the correct number of bits and tack it onto the front of our collection of bits. So when all is said and done here, we should have a collection of the bits that is a whole bunch of bits added together for our full bit space of our horizontal composite memory, right? And what will we do? We're going to return integer.parseInt of the bits, and it's base 2. All right, so that's what we are doing right there. So that's our read. Right? Already have this working, correct? We're staging something. Here's the decimal data we're going to write. We're going to get the binary string. Then we're going to pad it. So we're staging an already padded value. All right, for our write. Here's our read. So now we need to have SetState. So we'll steal this guy for SetState for our composite memory. SetState is going to take in the address, take in our Boolean, take in our when. Now, it's going to set the local version of those. But then it also needs to go and it needs to set all of the other versions of those. That is these three things in all of our internal chips. If we look at our picture back here, notice that when we send in an address and a ren and a when, they flow through to all the memory chips. Make sense? So they flow through to all the memory chips. So when we set it here, we set it for all of them.
So, for me, it makes sense how the memory chip works. I don't know how your code works. How do you know when it's treating chip 1 or chip 2? I don't really...
For our read, here's where we're reading from all the chips. This is chip 1, chip 2, chip 3, chip 4.
Correct.
Yep. And what I'm doing here is I'm reading the value from that chip, and I'm tacking it onto this collection of bits. So I'm getting because with horizontal memory, we're storing our value across, in our example, 2 chips. So I might have the number 7 stored in 16 bits across 2 chips. So I have part of the number 7 here and the other part of the number 7 here. Actually, what I'll have is the number 7 here and a bunch of zeros all the way over here. So what I'm going to do is, as I go through all my memory, I'm building up that string, gluing my bits together, and then I'm taking that giant string that represents probably a small number and parsing the integer out of it, assuming it's in base 2. That's where I get my actual answer.
And that's right, it's gonna be the same address probably.
Yes.
Okay.
Yeah.
Okay, so
Yeah.
okay.
Always the same address. So when we go in and we do a set state, I want to set the state for all of my individual memory addresses as well. Now, we probably want to have a way of setting that state. Think about this for a second. Actually, no, this should be okay, because if we've done a write, we're really not done with our write yet, because what we've done here is we've written at the global level. So here, I'm going to take this out of here just for now, because when we write, if we go back to here, we're saying we're writing data to our memory chip. And that's like data that might get written. We're staging this data to be written. But when we write something to this top level, we really need to immediately separate it into these other levels and send it in. We need to call write on all of our memory chips there. So they're all prepared to do their write. So what I'll do here is inside my write, I now have the correct number of bits in my write data. What I need to do is I need to grab this guy in bit width size chunks for each of our memory chips. Did I store that up here? Actually, it doesn't matter. We can use it from our memory just like we did before. So we have our data. We want to now grab pieces of that data, starting with our far right bits going into bucket 0 of our array. Correct? That's the little endian thing. So what we're going to do is we're going to have a we're going to say int curpos is equal to this dot write data dot length -1. That's the last legal bucket of our string of write data. So if write data is 16 bits long, this is bucket 15, 0 to 15. So we're going to set curpos equal to the very end of that guy. Then we're going to say for memory m in this dot the memory, we're going to do some stuff. What stuff are we going to do? We're going to write to this memory. So we're going to do an m.write, but we only want to write a certain number of bits. So we need to grab the next chunk of bits from, so string next bits. Just define a variable though. So we're going to say next bits is equal to, and what I want to do is I want to get the substring of write data from wherever it currently, from wherever it currently is minus my number of bits, like 8, for instance. So if I'm currently at 15, I want to get buckets 0, I guess would be 8 through 15. So I'm currently sitting here at the end of the thing. I want to get everything from this point back.
Yeah, minus.
Yeah. I can actually walk through this. Hold on. I want to look at something real quick. Yeah, this is 0 through 7 in this first one.
So it should be.
I can actually go from the front.
Go from the front, and then you just need to loop through from the either using for loop.
Yeah. But this might be kind of more fun to do a reverse substring.
I think just do reverse.
So, yeah, so what we're going to say is we're going to use substring on this guy. And so for this dot write data, dot substring, we can give it a begin and an end index. And the end index is non-inclusive. So my begin index I'm going to give it is I'm going to say cur pause minus m dot get bit width. And then my end index
Current position.
plus 1.
Your current position is already length minus 1.
Correct.
Substring.
I can do the math the right way, but this is non-inclusive in substring. It will not give me that bit from that last part. Substring says give me everything from this point all the way up to, but not including this. Okay, so we can do set cur pause the right data length, then we don't have to say cur pause plus 1 because we're already 1 off the end of it.
Just at the beginning.
Yeah, so I could say next bits like that, so that'll get me the last 8 bits, for example. But now I need to subtract 8 off of cur pause. So cur pause minus equals m dot get bit width. So that starts cur pause at the end. We grab our bits. Cur pause jumps 8 bits to the left. Cur pause jumps 8 bits to the left, so on and so forth. All right, but our next bits is stored here, and we'll say m dot write. M dot write takes what as a parameter? It's a int. So I'll write integer dot parse int of next bits. And that's in base 2. So I will write to this memory location the decimal version of the bits that I just grabbed, the portion of my number. And I will walk next bits. So I grab the last 8 bits. The next time through, I'll grab the second to last 8 bits because I'm subtracting cur pause each time. The next time through, I'll the third to last 8 bits, so on and so forth. All right, so that should fill memory up with stuff. So I've staged this high-level data that I'm going to write, but really what I've done is I've gone through and I've subdivided it into all my individual memory chips so that it's prepared to write at all levels through memory. All right, then lastly, I can set state. All right, and we'll set the current state of our composite memory here, but then we'll go ahead and we don't actually do this part. What we instead do is we do for memory m in this dot the memory, we'll say m dot set state to the address, ren and when. So set state goes through and it tells each memory to set its own state to those identical things. Okay? And we already have our writes staged appropriately across all of our memory. All right, make some sense? So now when we go out here to driver, I should now be able to, here I'll just comment this out. All right, I should now be able to say composite memory horizontal CMH is equal to new composite memory horizontal. And this guy takes in our constructor, number of memory chips, number of words, and bit width. So we'll start with something simple. So we're going to say 2 chips, 10 words, 8 bits, something like that. So 2 chips, 10 words, 8 bits per word. All right. So then we'll do a CMH dot write, and we'll write a 14 there. Now what I want to be able to do is I do want to be able to have my memory display itself. When I say memory display, what shows up? So display tells each word to display itself. Well, it'll be a little ugly looking, but that's fine. So
What do you want to display?
I just want to be able to see how it's split it, so we can view it. So I'll go ahead and I'm going to say public void display for our memory, and we'll say for memory m in this dot the memory, and we'll go ahead and say m dot display, and I'll just say int pause is equal to 0. Yeah, it's going to look extra weird with that, so I'll just leave that out. All right, so then we'll have cmh.display. Where is my part of my 14? Oh, I haven't written it yet, dear. All right, so now I need to say cmh.setState, and the state I want to put at bucket. I'm going to put at bucket 0 so I can see it at the top of the things. And then I want to set ren to false and when to true, because I want to be able to write. And I'm just going to do one more thing real quick just for readability. I'm going to do a system.out.println. I'm going to divide up the individual memory chips so I can see chip 0, chip 1.
By the way, can you making the number larger? 14 will not.
Yeah, I know. I just want to see. We should see it only in one of the chips and zeros in the other one. Then I'll make it larger. Right. I purposely picked a small one.
Okay. Cool.
All right. So here is our 14 stored in the right chip,
0.
and then here is the corresponding left 8 bits of that chip with nothing in it. Okay. Now, what's the biggest value that can be stored inside of 8 bits? Right now, we're not doing 2's complement stuff. So what's the biggest unsigned number we can store in 8 bits?
255.
255. So I need to have a number that's one bigger than that for it to spill over to the other side, right? So I will do, well, at least one bigger. So if I do 256 here, that's too big to fit in one memory chip. So I'll go ahead and run this. And now we see
Oh, cool.
that
Right.
we got that one extra value stored in our other memory chip. And then our first memory chip.
0.
Oh, right. Yeah, it is 0 because this is the 256 spot. All right. And if I go a lot bigger here, so I can have a lot more values. Now we'll see we have 100 stored there, 34 stored there in and of themselves. But these two things put together give us our bigger value. That make sense? So now in 16 bits, what's the biggest value we can store? 65,535? Come on, people.
I need a calculator. No, I don't know how to do math without calculator. Awful.
It's 2 to the 16th power. 65,536. So the biggest value is 0 to 65,535. So if I tried to do 65,535, that's the biggest value I can store. That maximizes my bits, right? I should have all ones. There's all ones there. There's all ones there.
So if you try to say if 65, the last is 6, then it means it will be 2 or 0, right?
Mm-hmm.
Too big.
Nothing stored. Needed 17 bits to hold that guy. Make sense? All right, but now, if I come up here, I run over to Best Buy, I get myself an extra memory chip.
Oh yeah.
Oh, nice.
Now I can hold it. I just upgraded my RAM.
Did you buy it online?
But does it
Download it
actually
online?
exist, say, 24 bits with architecture?
It typically is a power of 2, so 24-bit architecture would not probably be something you could buy, but theoretically it could exist.
Sure, I just say
Yeah.
in real.
In real life, it's usually a power of 2 because of the way they wire the chips together. It's less about whether they could and more about how they prepackage chips in powers of 2.
Yeah, that's it what I make it.
So really, this would be a 32-bit value, right? Which could hold up to somewhere in the ballpark of 4 billion. All right. So when we write something here, you know, I can put 4. Let's see, it's 100.
You can put
3, 4, 5,
9
6.
digits after 4.
Yep. All right, and I think I need to make this like a 0 because that other value might have been a little bit too big. So this should be using a pretty good chunk of our space. Make sense? All right. So really the limitation of our program right now is that memory is, because we are writing integers for human convenience, we are limited to the size of the value we can pass in here. Because Java's int can't hold that size value. Our memory can. We built something in Java that can hold things better than Java can hold them. Make sense? So what would I have to do here? Well, I'd have to either put that into binary, you know, give it the bit input, or I could do it as a big integer. But big integer is still going to be, well, actually, would it? Can I do a bit? That's an interesting question. Does big integer support 2 binary string? Big money, big money. 2-byte array. I think we could actually pull it off with 2-byte array. Oh, here. Returns the string representation of this big integer in the given radix. Nailed it. All right, so now we've created our own data type. This is going to be awesome. So our write here for big inner or for this guy's going to take a string.
So what is the maximum size that you can?
An int is 32 bits, which is negative 2.1 billion to positive 2.1 billion. But a string can hold a lot bigger. It's going to be some sort of limit. It's probably, you know, the size of long or something like that for the number of characters.
I did try to create a zero memory yesterday in stream, and I ran out of memory in Java for the day. And the number was let me see if I can go back to the number. Of course, everything broke. I had to change.
All right, so big integer lives inside of java.math. So now I've built my big integer here. And I'm going to get the binary string of this guy right here. So I can say bi dot, what was it? Get, or two string. Two string radix. Okay, so we're going to say bi dot two string, giving it 2. So now it'll take in any size value, pad it to the number of bits that I support. Oh man, this is ridiculous.
You create something.
So now I come back in here to driver. This guy's going to take in, so it currently doesn't support that because that's too big. So now I'm going to pass this guy in, run it, and now we hold that memory. And let's just bang on the keyboard for a little bit. Okay, so really big value there. I don't know how many memory chips I'm going to need, so let's just, we'll just make it 10. I think 10 should be able to hold that number. Oh, just barely. I actually did go on to my last chip. That's awesome. So we've implemented horizontal memory in Java, which allows us to store arbitrary size integers as binary strings.
So
That's actually really good. We should publish this.
in real situation, does it really have any case like say if there's a commercial computer having that many size of the bit width of memory commercially?
Today?
Uh-huh.
I get what you're saying. You're basically saying, would it ever make true sense for there to be a horizontally organized memory chip that allowed you to have this many bits?
80 bits. No,
Yeah.
your case is.
Yeah. So yeah, I have an 80-bit width thing. Yeah, man, I can go to 100. And just hold the key down.
All the atoms in the world may not having that many numbers.
Boom. Man, look, we're not even touching our memory chips here. Look how far we have to. We're not even there yet. Oh, I'm not even to data.
There are 1,000, like a thousand.
We're in data. We got data. You never know when you might want to store that many digits. Oh my gosh, that's actually pretty fun. All right, so that's we need to do a read, right? I'm going to go back to a normal number because we're not going to know whether that's correct. is the punchline. So we'll go back to our 2 by 10.
Now you're going to read.
Yeah, so I'll write a 40, set the state, then we'll go ahead and do a CMH set state, give it the address of 0, true for when, false for when, and then we'll do system.out.println cmh.read, which should give us that 40. There's our 40. And if we increase the number of chips greatly, so we have a really expensive memory chip that we only store a 40 into, we still get a 40 out of it.
Okay. Only using the pointer.
Wasn't this one fun?
1% of usage.
Didn't you guys have fun with this assignment, this one? This should have been a blast.
We're laughing yesterday. Yeah, we were laughing very much.
We were laughing after we stopped crying.
Our code's beautiful. You're gonna love it. Oh, yeah.
Good. All right, so does that answer the next question? Oh yeah, so then the last one is composite memory vertical. So pretty similar to this. That's in the next section of the book.
That's my problem. I can't see similarities on this. I can't understand. It's like a.
Who?
I can't understand that thing.
Oh, this one?
Yeah, like.
This is very simple.
Well, that makes her feel better. This is so easy. I think the problem is that this kind of goes back to what we talked about the previous class, is this looks way more complicated, right, than this one does. Just at a glance, you have all these straight lines coming through here. It kind of just makes sense. So let's kind of walk through how this guy works.
Yeah, it's really like the third step that made me very confused.
Okay.
What it's saying.
Yep.
This is just stacking together.
Well, right. But the issue is that you have a whole bunch of stuff here that I'm guessing you were trying to emulate.
Think about it, just make
So when we have our write data,
How you don't think about it if you have to write a code?
so here, we're writing data. This is just writing 8 bits. So understand what a vertical memory space is going to let us do. We don't get to store bigger values like we're doing right now. Right now it's kind of fun because we get these huge values, but we are still limited on the number of values. So no matter how crazy I go with this guy right here, I am stuck with 10 unique values. They can be 200 chips wide, but I get 10 of them. Vertical memory allows me to have way more than 10. I just can't store bigger values. Now, the reality is our memory today would be a combination of these two. We would give ourselves the ability to store bigger values and more of them. But we're just keeping these completely separate. All right, so we're going to write just our 8 bits of data. So we're back down to kind of normal human numbers, let's say. So we're writing this guy, and just like we had before, when you write here, you also write here. So we have collection of memory, we're writing to both places. Same thing. When we read, we're reading from both places. So now let's kind of look what's happening over here with these pieces. So when we set the state, that's this function right here, right? So we set the state. We always give the address to both things. Let's see. So address comes off of this. So what is this guy? This guy is a decoder, right? So he's going to take in a single input and he's going to split it into 2 outputs. Now, what is his single input? His single input is this address. Make sense? So this address comes in, and what do we do with this address? This address comes into the decoder, and it serves as 2 inputs here. So this value, whatever that address is determining which memory chip does this guy go into. That's what we're accomplishing here. Because vertical memory says, I now have a memory chip on top of another memory chip. This is address 0, 1, 2, 3, 4, 5, 6. So my later addresses are on deeper memory chips. So it's not the same addresses across multiple chips giving me bigger values. Now it's more memory addresses split across memory chips. So we can think of this guy as a big array. Okay? So what this dude right here is doing ultimately is he's saying, which chip should my address go to? if I put in address, so what are they doing? This is, did they give me an example of what this guy is? Is he 1,000 or the 4096 like they did for the other ones?
Look at the question below.
Uh,
Yeah. What is it?
oh, whatever. So this would be 0 to 4095 would be addresses up here. This would be 4096 to
900.
yeah, whatever the thing is.
8,001.
All right, so they're divided. Now this is the architecture that allows this to happen through a signal. So we're taking an address in here, and we're taking this decoder, and if you remember back to what decoders do, decoders take an input and based on a switch give you outputs to two places, right? So here, let's go back to our decoders.
So
Now,
the address there are different for both, or the address are the same for both chips there too?
correct. Well, okay, no. I get where you're confused. Let's just look at decoders real quick,
Okay.
and then we'll come back because we want to understand the pieces that we're working with, right? Okay, so this is back up here in 5. So decoders are the alternative to a multiplexer, right? The second cousin, let's say. So here's our decoder down here. So a 2x4 decoder takes in some inputs, and depending on what those inputs, right, and what we have here is a 1x2 decoder, okay? But we can just look at our example here of a 2x4 decoder. So this decoder takes in a number, and that number is, this is our truth table for it. So 0, 0 is going to output to 0, 0, 0, 1. So it's going to have 4 total outputs here. So it'll output a 0 here, a 0 here, a 0 here, and a 1 here. Otherwise, it's going to be 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. So depending on what the input is here, says which of these things fire. Make sense? So that's what a decoder does. All right. So now we go back here to our memory thing. What was that, 6.3 something? Okie dokie. All right. So we see our address come in, and our address goes directly here. So we write address here. But our address also comes in here as a 1. So notice this is a hard-coded 1. All right. So what does this decoder has 2 states, correct? So the state of this decoder is either so this would be the other one, this would be a 0. This would be a 1. So if a 1 comes in here, a 1 fires out of here. That makes sense? So we're going to take this signal here, and this signal generates a 1, guaranteeing that this stuff fires here. This guy is a 0. Okay? So we have a 1 coming out here, we have a 0 coming out here. So we've taken this one signal to deliver 2 separate things here. So now, what ends up happening? Depending on what my address is, how did this guy get the address? This address here is the same address that's delivered to this guy. They actually made it a little confusing here by not showing that connection. All our memory chips get the address input, but it's only showing it coming here because this guy takes 1 bit in. This is way too big for an address, so that's why it's always a 1 here. So we can assume that this address gets set to the same thing as this address. We might not use it. Go ahead.
I think it is, we can say, now the 31 bits of address has split into two numbers. One number is for the decoder. The rest go to
the 0 to 29. That's why you always get a 1 here.
Yeah, and the decoder used to combine with read and write. So
correct, but this guy right here is going to ultimately have the same address as this guy's going to have up here.
But because the
Yeah.
read and
What
write
he's saying is that our address here has been slightly ripped apart. So our address came in as 30 bits. Well, really, it came in as 31 bits, let's say. 0 to 29 continued on to this. Bit 30 traveled down to here for this decoder.
Yeah.
So we break up our address, so we've lost some stuff, but the first 30 bits of it are going to be the same. All right?
And I think if we think about software information, it will be easier because the first bit
Our software is going to be way easier.
is the
Yeah.
is the array, is the index of the array because we have multiple chips. So we have one.
It's
bit
going to be the
for
index of which memory chip is
Yeah.
in our array.
And so
Yeah.
software is even easier.
Yeah.
to
So what he's
implement.
saying here is this. When this is a 1, that tells us we will go to our second bucket. Bucket 0, bucket 1. Go to our second bucket of our array. That's what it ends up being. But we're going to work backwards from the complex to the simple. All right? So what we're seeing here is if we were building this memory out of hardware, what would we need to do to make sure we selected the correct memory chip as we came through here? All right? Just like before, we have an address, we have a read enable, we have a write enable. Just like before. One way or another, that read enable, that write enable is getting set to all of these things. All right, so we're getting that data to it. We're getting the address to these things. But when we do a write or we do a read, it's only going to write a read to the dude who's currently living. The memory chip that's been selected. All right, so all of this life. So what kind of gates are these guys?
This is
And gates. So both of these need to be 1. So this needs to be 1 and 1 delivered to this in order for this to fire a 1. Same thing here, same thing here, same thing here. Where's the source of these guys? Well, we have our top level Ren comes in here and he delivers to this top one for the Ren and also to this one. So whatever the Ren is here, it's basically directly delivered to both of these Rens. Directly attempted to be delivered to both of those Rens. It has to get through this gate, right? And the AND gate only opens the door if both things that come to it are 1s. But whatever the Ren is here, gets delivered here and gets delivered here.
So can you hit start and go to the third step? I just want you to explain what they mean by that sentence on the third step.
Okay.
jump steps.
If an address is less than 1 gigabyte, start with 0. The top member should be activated. Is that what you're asking?
Yes. Why is it saying if an address is less than a gig? What
Because
is like
yeah, so
an
it's
address?
what he had just explained. This idea that this first thing here, it actually is related to what we were just looking at. Is we got numbers that were bigger and bigger and bigger, and all of a sudden it spilled over to our next chip. We got that 1 bit there.
No, yeah.
So the idea is that if each of these are 1 gigabyte chips.
Yeah,
2
because
power of 30.
Oh, hold on. We will keep it simple.
No, but I know that. I know what 2 power of 30
Yeah.
is 1 gig, 2 power of 31 is going to be 2 gigs. So my question is, are the addresses going to stay the same even though we are dividing by the size? That's what made me confused. Is the address number are going to stay the same on both chips that are connected?
The address number will be. It's which chip do we go to?
Okay.
That will change. So if the address is less than, this is, I kind of get what you're saying here. This is a little bit deceiving the way they write this. This is if the address is less than the allowable addresses on a 1 gigabyte chip. That's what it's really saying.
But it's just the 2 power of 30.
No, but that's too mathy for this. What we want to do is this
That's
thing.
not what it's saying.
Yeah.
Maybe there are the two
Yeah.
ways. Actually, it's the full size of the memory. It's not
Correct.
talking about the address.
So
Each
If
address
you
gets
think
only
about
8.
if you think about 0 to 1 gig is on 1 chip, then
yeah, she already said that.
that's
She already said that. She gets that part of it.
Okay, what is the size of an address in a memory?
In our memory here,
Yeah,
8 bits.
yeah. So what is saying
That's
there?
it.
If an address is less than a gig, that's what is making me
Yeah, this is a poorly written sentence. You're right. This is a poorly written sentence. So this is saying if the addressing of this guy, what's supported, if it's less than 1 gigabyte. So we have 2 gigabytes of RAM here, right? So we have 2 gigabytes of total storage because that's what vertical memory gives us. So this sentence in a really bad way says, if your memory is found in the first gigabyte, it's in chip 0. If it's found in the second gigabyte, it's in chip 1. That's what it's saying. Now, the math behind that translates to what he said earlier, where this bit of your memory address would dictate whether bucket 0 is the part of your index you go to, or bucket 1 is the part of your index you go to, or bucket 2 is the part of your index you go to, because it'll go through some more decoders. But it tells you what your index is based on this wiring. For us, because we're focused more on the software side of this than the hardware side, we want to understand the concept of how these things work, not necessarily be able to build them. The idea of going here, actually, is it the final step? Is that what I want to see? Yeah, this guy. So the idea of going here, what I'm telling you is all this crap in here ultimately, makes the selection of which of these chips do I read my address off of. And then I get my value. It works just like normal memory, but all of this wiring is the hardware version of the algorithm that says, which chip am I dealing with, and am I reading or writing from it?
No, that part was easy. I was just not understanding why it was saying if an address is less than a gig, because an address is actually 8 bits.
Yeah,
So
it was a poorly worded.
And
yeah.
that's why I said, for example, the string my memory to 2 gig and it broke.
Yeah, no, I get it.
Yeah,
I get it.
So that's
Yeah, it's worded funny. Yeah.
Okay.
I mean, it only makes sense in the context that they say your each chip here is 1 gigabyte, but they could have said it differently. Yeah, I don't know. It's a weird sentence. You're right.
I think it is say, if we are only using 8 bits, definitely you cannot map in a gigabit of
Well, right, but the way it was written, it kind of sounded like it could.
It is
yeah.
not really meaning that we only using 8 bits
Yeah.
to manage the memory.
Part time, yes, no? If you want to write or read, you're gonna use only address to use, and
Yeah.
it's 8 bits. So you can't really use a full gig at once.
Yeah, but for the purpose of you can't use a full gigabyte on vertically organized memory. Yeah, so so when you look at something like this is extra interesting from a hardware perspective. But from us, so we could follow this with a bunch of examples and ultimately see that, okay, once things pass through these AND and OR gates, we end up selecting the correct bucket of memory that the stuff is in, and the right ren and wens get set. And then when we do a read, it reads from the right chip. See, this guy connects here. It also connects here. When we write to the right chip. This guy connects here. It also connects here. So in software, we don't have to worry about writing we could. It would work that way. But we don't have to worry about the decoding of it. We can just ask the question, here's the address you want to write to. Where would that be located? Is that in the first chip, or is it in the second chip? Is that in the third chip? Because you know the size of your chips. Make some sense? All right, so when we go back into our composite memory vertical, I see, yeah, I just looked. All right, so composite memory vertical. This guy's going to work very similarly to what we had up here. We're going to still have memory. We're going to still have a bit width. We're going to still have a when and ren. We're still going to have an address. We're still going to write data. The data we're writing is always going to be the same size. So it actually, our nature of decomposing data becomes a lot easier. We don't have to build this new bit string back up. All right, and I'm just going to kind of talk through this so we can talk about the exam here in a few minutes. But, the idea here is that, so I'll kind of point out what would change. These things are all going to remain the same. When we build our composite memory, num chips will remain the same, Num words would remain the same. Bit width would remain the same. This is information about the individual memory chips we have. Num chips indicates the number of unique addresses we have. As opposed to on a horizontal, it's the size of the values we can represent. This is the number of values we can represent. So for horizontal, it's this times this is the number of bits that we can represent. In this guy, it's this is the number of this size values we can store. That makes sense? So we'll still fill up our memory with a bunch of memory things that are num words, blah, blah, blah. We don't need to do this bit width thing here because our bit width is our bit width. Every memory bucket defines what every word defines what the bit width is going to be, because in our example, it's all 8 bits, for example. We don't, two 8-bit memory chips don't give us a 16-bit bit width. They give us an 8-bit bit width, but just more of them. All right, so this guy won't have to be a thing. This is the same, this is the same. For writing, when we write something here, we're going to just store the value that we're writing. But what we're going to do is we won't have to do any of this crazy stuff. We'd only need the big integer portion of this if we wanted our memory chip, an individual memory chip, to be some sort of colossus where it's no longer storing a bit width of 8, it's storing a bit width of something greater than 2.1 billion. That's a lot of bits. So we probably wouldn't need a big integer for that guy. So the idea would be is we would go through all of our memory and write that data to each one. So it's in preparation to be written just in case that's the memory chip that gets selected. Okay, so for loop goes through, writes everything to every memory address. All right, we don't need to do any of this crazy stuff where we're like decomposing, from 128 bits into different little parts. Here's the value, we're writing it everywhere. Trying to write it everywhere, so when it does get written, it gets written to the right place. All right. Similarly, read, it's going to check whether we're read enable. If it is, it's going to have to figure out which of my buckets. So this is the selector thing. Which of my memory addresses am I reading from? So if this is true, I don't have to do any of this crazy stuff, recombobulating my bits like I did before, where I was taking substrings and things like that to put everything back together. I don't need to do that anymore. Now, I just go to the right place in memory based on the address that was delivered. So bucket 0, bucket 1, bucket 2, whichever the selectors, whichever my memory buckets I should work with, go to the correct address in that guy, okay? And then ultimately get the value. Just like our normal memory chip, we're not doing any sort of having to piecemeal values back together, okay? So from that perspective, it's easier. Okay, so it's easier to write, it's easier to read. Now, where things are a little bit more difficult is the set state, because that's where we need to properly select the address. All right, easy part of set state. Where's my set state? So we're going to take in this address. Now, this address, if we just think about this as our 2 memory chips, this is a bucket in that array. That address is either going to be in the first one or the second one. We can ask an if statement on this based on the modulo size of your number of bits to give you the bucket number. So if if I had 4096 like the book uses, or 1024, whatever it is, I think 4096 is what the book's been using, right? Yeah. So if I take whatever that address is and I take that divided by the number of addresses per memory chip and look at the remainder, that'll tell me which memory chip is the right one. Mm-hmm. That gives you your bucket 0, your bucket 1, your bucket 2, so on and so forth. Make sense? Mm-hmm. And then we can, do our set state for the right memory chip and all that jazz. And then the next time we do a read or a write, it'll write from the right place. That kind of makes sense. So our version of this crazy stuff here is taking the memory address and modding it by the number of unique buckets in each memory chip. That gets us our bucket 0, our bucket 1, our bucket 2, our bucket 3. All right. So from a software perspective, this is actually the easier of the two to implement. From a hardware perspective, this is the harder one to implement because you have to do, that whole modulus math thing I just mentioned, which is really easy to write software for, is a lot harder to fake in hardware. This is the equivalent little program for calculating the modulo of a memory address. Does that make sense? That's what we're actually looking at here. If we abstract this piece out and we just say, here's crazy hardware I'm looking at, what problem does that solve? It calculates the modulo of this address to ultimately select which of the things. All right, make some sense? All right, so with that in mind, let me go through and point out. So what I'm going to do is I will try to put it up tomorrow so you have as much time as possible to do it, but I'm probably guessing nobody's going to look at the midterm until next week or probably even the week after, but I'll put it up as soon as possible so you technically have as much time as you want. So I'll put a midterm up. It'll be on Blackboard. I'll design it to take probably an hour, but I probably will give you like 2 hours to take it or something like that. So I don't want it to be a time constraint type thing. But I also don't want to give you, a month to Google everything. So.
Wait a second, is that so hard? You would give us such a Google?
Well, I mean, you're doing it on a computer. I can't actually keep you from Googling, right?
That's
I mean, I can tell you don't cheat. I'm just saying I can artificially go in there and say, I typically don't ask questions that are real Googleable anyways, but
doesn't mean it will be even harder.
Okay. I'm not taking that into consideration, but I'm just saying that the amount of time I put on the timer for it should not be prohibitive for the amount of time it should take the exam.
Is there anybody you could do like 2.5 hours? Because I know I was talking to Ani, Maddie, and Jordan, and they were saying that for 518, you had told them you were going to give them 4 hours, but you only gave them 2, and they were saying that that was a little tight. Like, I think Jordan.
Well, but I'll think about it. I'll give you plenty of time, whatever that is. So let's talk about which things in here I think are most important versus what things are least important. In general, the questions on the exam will not have you do a lot of stuff with hardware. Having said that, if we just kind of start on the hardware section, let's look at which things you should understand. So I would say that you should understand from section 5.2, be able to differentiate between decoders and multiplexers. There could very easily be a question that deals with those specifically. I say, show me the truth table of a this by this decoder, or the truth table of a this by this multiplexer. You should know what they are and how they function. Okay? I wouldn't ask you to put together the circuit to actually create one of those guys with a whole bunch of nasty looking AND and OR gates under the hood, but you should know how those guys function. Okay? Today's homework, you wrote a multiplexer, and that I don't think that was overly horrible. So from this section, I would say you should know how those work, decoders and multiplexers. I would say you should also know how registers and register files work. Again, at the high level, how these guys function, and if I showed you a register, for example, and you had a number of bits come in, what are the conditions that have to occur for something to actually get set here, and that kind of stuff. So understand if we treat these as a piece of software, how do they actually function? Make sense? All right. So let's see if there's anything else I want from that hardware chapter. I would say that's going to be good enough. I am very interested in the MIP stuff, but I'm interested in it more from the software side of things rather than the hardware implementation of these software instructions. Even though it's not really any different than the stuff we've been talking about, For us, it's a lot easier to talk about something from the logical equivalent software versus, hey, here's the crazy stuff we had to wire together to get the same truth table, where the inputs I gave to my software gave me a result, and the inputs I gave to this hardware gave me the same result. So two things that have the same inputs that produce the same outputs are logically identical to each other, even if they accomplish the task in completely dissimilar ways. Make some sense? So this stuff in this chapter really goes into how do you create those hardware circuits that ultimately produce the truth table that you're looking for. So if you think about yourself as a hardware programmer or hardware architect, you really are taking the skill of computer programming and saying, okay, these are my inputs, this is my desired output. What programming language logic do I have to put in the middle to solve the problem? When you start off as a computer programmer, you're not very good at that. Over time, you get better and better and better at working with those tools, working with the primitives, creating variables, asking questions with conditionals, writing loops for repetition, all this stuff, right? We get better at those tools. So the tools for us as computer programmers are variables, conditionals, and loops. Just like if we're a hardware programmer, a computer hardware architect, we have our inputs and we have our desired outputs. That's equivalent to a software programmer, right? But the tools we use to accomplish that are no longer variables and if statements and for loops or any kind of loops, right? Now they're AND gates and OR gates and multiplexers and decoders and micro memory. So, kind of our memory pods for storing a little piece of information like a register, that kind of stuff. Okay. So we solve the problem in terms of those. Now, our program here, our undergrad program, is not a hardware focused program. So you come into our program here and you end up doing a lot of software stuff. So you get a skill set built up in the software primitives. That's why that's easier for us to conceive of. Now, if you had done a computer engineering type program, you would have done some software stuff, but it would have had a lot less business focus. And what you would have done is you would have spent, instead of some other classes you would take classes on practicing the hardware programming with the registers, the gates, working with electricity, clock timers. Those would be the tools you were used to solving the problems with. And over time, you would get better at working with those tools to the point where if I said, here's the truth table, this is what your inputs look like, this is what your outputs look like, you would be able to slap together a circuit pretty quickly that gave you that because you have experience working with those tools for solving the problem. That makes sense? So this exam will not focus on that skill set. In fact, I would say I won't ask anything regarding that skill set. I do want you to know what a multiplexer is and a decoder is and what a register is and what a register file is in terms of its hardware functionality, but not from the I created one perspective. All right? Make sense what I'm saying with that stuff? Mm-hmm. Okay. So from chapter 5, basically just 5.1, 5.2, 5.4, 5.5, and more of the understanding how those components work things. From our most recent section, from our memory section, which is what we dealt with here, I would say something pretty similar. We should understand how a memory chip works, how composing memory works, horizontal and vertical memory, how that works, okay? But not necessarily how it works from the software logic side of things, not necessarily the hardware implementation of it. I promise you the hardware implementation of it is not any more difficult than the software implementation of it. If we were talking to a computer engineer who loved hardware, he might be sitting here and say, oh, I can't do the programming side of things. I wish you could just give me a soldering iron, I'll just go to town. That might be the easier thing for him because that's how he grew, he learned. He learned in terms of solving problems with those primitives. Okay. So I will not deal with cache or anything like that from in here, because we didn't really test with it on our homework or anything, and this is still pretty hardware-y. I think the memory stuff we talked about covers our bases for the memory stuff. So composing memory, so general memory, composing memory, vertically and horizontally. Okay. And really, this chapter 7, this is actually already covered when we did the MIPS stuff. This is the hardware side of input and output, right? We wrote I/O into our MIPS interpreter, our MIPS implementation. So I would say kind of the same thing. I probably won't ask anything from this section directly from the hardware perspective. But what we see here is a repeat of what's talked about in the MIPS section for how this works, but you're seeing the hardware implementation of us just magically writing something to a certain memory address, which puts it into read mode, right? Okay, so it's not that the stuff from chapter 7 here is unimportant. It's the hardware explanation of what we did in like chapter 3 or something like that. Yeah, MIPS assembly part 2. Was it part 1, chapter 2? Yeah, input output. So chapter 7 is basically the hardware description of 2.10. 2.10 says this is how it works at the assembly language level. Chapter 7 says this is how we implement that under the hood. The magic tricks that you're calling at the assembly level in 2.10 is what's happening in chapter 7. Okay, so I can't imagine asking hardware questions from 7. But I will expect you to understand the I/O stuff from the software perspective. So if you're focusing on studying for this, obviously be able to work with bits, all the bases, conversion, stuff like that. I should be able to give you almost an entire question and some base and have you convert it. That would actually be a fun question. Like literally write it in binary, ASCII. Have you converted into the individual? I just spent 2 hours translating question 1. I am out of time. All right. But in any case, you should be able to work with bits in all the different bases. You should be super comfortable with that. I should be able to throw any conversion at you. It should work. The MIPS stuff from part 1, chapter 2, any program. I should be able to ask you to, and I'll probably do that, have you write MIPS kind of programs in our in MIPS assembly, similar to what we did for that one homework assignment, right? Where I had you you write in a couple of numbers and you loop through the values between the first number and the second number, that kind of stuff. Okay, you should be able to write assembly for simple things like that. I would probably focus on an exam. There will probably be a question dealing with, I/O on the software side. But I probably, for most questions on an exam, I might say, you can assume that these 3 registers have these values in them.
Okay.
Given that as your starting point, write the code that would accomplish some mathy task or something like that. Make sense? Rather than have you do I/O on very many questions. So I might ask one question about I/O to show me that you understand how I/O is accomplished in a processor. But you wouldn't have to do I/O for questions, the programming questions. I would just give you registers with values and say, do something with this. Okay, so that's chapter 2. Chapter 3. I would say 3.1 through, this is how we stored it, right? I would say 3.1 through 3.3. All that's fair game. The program stack, I'm not going to ask you questions about. Not that it's not important, it's actually more representative of our modern hardware, but we didn't implement anything dealing with the stack. So it's, the stack gives us extra memory when we start running out of registers. We've operated for all of our assignments under the guise that trust you won't run out of registers, okay? Stack's important. I'm not going to ask you questions about it because we didn't really dig into it, all right? You should, though, be able to work with procedures. That's why, so this is a program stack for subroutines. So we actually handle subroutines in the previous chapter then, I'm guessing. Was that in 2? Oh, yeah, subroutine instruction. Yeah, so 3.1, 3.2, 3.3, that's fair game. Nothing from 3.4. I probably won't ask you anything from 3.5.
So basically, we just need to program in assembly.
I think that's fair.
No scheme.
Program, I don't know. It could be.
I'm just, don't give him a yes.
Make up assembly.
All right. So 2.1. So anything in chapter 2 is fair game. And then the first 3 sections of chapter 3. That's what's in your toolbox for MIP stuff. All right. The C stuff, converting stuff from none of the optimization stuff. So I won't ask anything about optimization, like the better way of writing something. We're going to focus on 4.1 and 4.2 because that's what we implemented.
Expression.
Yeah, we implemented these 2 things. Remember, this was the shunting yard thing.
Mm-hmm. But what do you want us to focus on that?
Yeah, so I don't want it to be memorization. So I might say that you should be able to look at something like this and write me equivalent C code. But keep in mind here that you get to pick the name of your variable, right? So if you have something like this, this should flag you as like, oh, I'm loading a register. I'm zeroing out a register. I'm putting some, a memory location in it. That's probably creating a variable.
Yeah.
All right, so you can name your variable whatever you want as long as they're uniquely named. Then what am I doing? Oh, I'm loading an immediate value into a register. Okay, and then I'm storing it at a memory location. That's giving a value to a variable. So I should be able to give you some assembly code like this and say, give me some C code that would be the potential code that would produce this assembly, something like that. So if I showed you this exact assembly here, it would be reasonable for you to say int b equals 7. Because nothing in here dictates that the variable name must be X. But this first line says create a variable. The second line says load that variable with a value. Make sense? So I should be able to show you assembly code and have you be able to look at it and say, this is what that does. And here's the C, even the rough C equivalent to what that guy is. Make some sense?
Can you post your last code?
Yeah, I'll put it on GitHub. Okay, so that's 4.1. So I'll probably focus on 4.1 and 4.2 from here. Conserving registers is really an optimization. This other stuff, I'm going to say would be fair game, but I'm only going to ask you questions dealing with the things that we implemented. But if I wanted to make sure you really understood it, I might just ask you more complex questions in this zone right here. So I would say focus on 4.1 and 4.2 to make sure you understand that and you can read assembly and give me equivalency.
Okay.
All right. We already looked at 5. We already talked about 6. And I pretty much won't ask anything from 7 because we cover it in 2 from the software side. Okay. Does that make sense?
Yes. What is the due date for the test?
Before class starts our next class. So we don't have class next week.
Halloween.
Yeah, we don't have class next Thursday, so 2 weeks from today.
31st.
So it's effectively the homework that's due, on Halloween. So 2 weeks from today, and then so 2 weeks from today we'll start our data science stuff. What I will do though is I am going to give you a reading assignment to read chapter 9 to start the data science stuff. You have 2 weeks to do it, so manage your time. Take the exam, and I'll put this up because there'll be a. Actually, so there won't be something to submit for your reading assignments in here. I don't do submissions for reading assignments in here, right?
Nope.
Okay. So for next class, I'm going to expect that you've read chapter 9 because we're going to start going over chapter 9 in class and doing some stuff. Okay. So read chapter 9 for next class and complete the exam before class starts.
Yeah. And we're gonna work with Python, right? We're gonna learn.
Is that what the book uses?
This is Python for data visualization.
Yeah, I'm guessing yes.
So let's
Whatever the book says, that's what we'll do.
Awesome.
All right. Sound like
R now.
sound like a plan? Well, R is just Java.
Ours is easier.
Well, it's Java syntax.
But they say that Python is going big.
Okay. So we should do R?
No, it doesn't.
I would prefer R.
All right. All right, so everybody's clear? Chapter 9 for next class. Have it read. We don't meet next week. We meet in 2 weeks because I'll be in Florida next week. And then have chapter 9 for next class, and we'll start doing data science stuff.
Is chapter 8 part of the data science stuff?
No, chapter 8 is your MIPS simulator.
Oh, okay.
Yeah. All right, questions, comments, concerns, bribes. All right, make sure you give a donation to Mr. Gonzalez's big, beautiful black hands out there.